Thank you to the organizers for putting this workshop together and for the invitation. My name is Silvia Biscoveanu. I'm a new faculty member in the physics department at Princeton, and I've just learned that I am the token gravitational wave / LIGO person here. And so I'm going to try to, carry this torch and represent the LIGO results as faithfully as possible. But yes, feel free to stop me with questions. Okay. So we can now probe gravitational waves across many decades in frequency. So if we take a look at the sensitivity of key facilities to gravitational waves as a function of frequency here, we can see that on the low mass end, we have pulsar timing arrays, which represent an international collaboration that is using radio telescopes to probe gravitational waves in the nanohertz regime. And we think that these gravitational waves come from the slow in spiral of supermassive black hole binaries. I will not be saying anything more about nanohertz gravitational waves or supermassive black holes. So I look forward to hearing more about the spins of supermassive black holes from the other experts in the room. And on the high frequency end, which is where this talk will be focused, are the ground-based gravitational wave detectors. So we currently have a network consisting of 5 operational detectors. There are the 2 LIGO detectors in the US, one in Hanford, Washington State, and one in Livingston, Louisiana. There's the Virgo detector in Italy and the Japanese detector Kagra. And then there's also a smaller detector in Germany that's mostly used for research and development. And then ground has been broken on a detector that's under construction in India, which will be very similar in design to the 2 LIGO detectors. So the ground-based gravitational wave detectors are sensitive to gravitational waves in the frequency range between about tens and thousands of hertz. And all of the gravitational waves that we have observed in this band so far, we think come from the merger of compact object binaries consisting of some combination of black holes and neutron stars. So how do these stellar mass compact object binaries actually form? Well, there are 2 main theoretical formation channels. On the left, we have the idea that these objects are lifelong companions, and this is called the isolated binary evolution channel or the field formation scenario. And the basic idea is that you have 2 stars that are born together in a binary. They evolve together their whole lives. Eventually, one of the stars goes supernova to become a black hole. The binary stays together throughout this process until eventually both objects end up as black holes or neutron stars. In this case, we're going to talk about black holes. On the other hand, however, you have the possibility that the compact objects are more like social butterflies, and we'll hear much more about this from Carl tomorrow. But the general picture is that you have lots of stars and compact objects in some kind of dense stellar environment, like a globular cluster or a nuclear star cluster, and they're constantly undergoing dynamical interactions until eventually some of them end up paired in binaries that are close enough that they can merge within the age of the universe. And so these 2 formation channels predict very different signatures in the spins of the resulting binary black holes. So for the isolated evolution scenario, we expect that the spins are going to be mostly aligned to the orbital angular momentum because of tidal effects in the stellar progenitors. This means that it's really hard to get tilt angles with respect to the orbital angular momentum that are greater than 90 degrees for systems that are forming in this isolated evolution channel. Then we would also expect that the first-born black hole will have small spin because of efficient angular momentum transport in the stellar progenitors of these objects. Basically, what this means is that all the angular momentum is stored in the outer layers of these massive stars. As they evolve, these outer layers get blown off, leaving behind a slowly spinning core that collapses to a slowly spinning black hole. However, the second-born black hole can potentially be spun up, again, due to tidal interaction. So this would occur at the stage where you've got one evolved star and one already formed black hole. And at this point, tides will synchronize the rotation of the star with the orbit of the binary, and that star can collapse to a more rapidly spinning black hole. And then We are also potentially interested in the azimuthal angle between the in-plane projections of the black hole spins. This is called phi 1, 2. And so for systems that form in isolation, it's possible that they will be caught in or near a resonant configuration due to an effect called spin-orbit resonances that I'll talk more about later. And so in this case, you would expect that these systems would preferentially have their azimuthal angles either aligned or anti-aligned. Now, in the dynamical case, the picture is a little bit simpler because there's generally no preferred direction in the cluster. And so the spin directions are going to be scrambled by all these dynamical interactions. And so in general, we're going to expect an isotropic distribution of the spin angles. And for the magnitudes, because of this efficient angular momentum transport in the stellar progenitors, we would expect low spins except for in what are called hierarchical mergers. And so this occurs when the remnant of a previous merger is retained in the cluster and it actually pairs up and goes on to merge again. So because of the conservation of angular momentum, that merger remnant will have a spin of about 0.7. And so if we observe it merging as a higher generation merger, we would infer that that object has high spin. And so the idea is that we can look for these signatures in our data to distinguish between these two formation channels and learn about how binary black holes form, both for individual events and for the population. So we are now reaching the end of the fourth LIGO Virgo Kagra observing run, and we chunk up our observation periods into these observing runs. The first one began 10 years ago now, almost to the week on September 14th, 2015, with our very first direct detection of gravitational waves. And in between each of the observing runs, there are upgrades performed to the detectors. And so you can see in this plot that shows the cumulative number of detections as a function of time, there are these significant changes in the slope. And that just means that the detectors have gotten better. And so last month, we released our fourth gravitational wave transient catalog, GWTC4, which includes all of the confidently detected gravitational wave events up until the end of 04A. And so we are working really hard to analyze the data from 04B and C, and that should be coming out in the next year and a half-ish. So in addition to our watershed first direct detection, we have completed our portfolio of the various kinds of gravitational waves from compact object binaries that we can detect. So 2 years later, we had the first binary neutron star merger observation, GW170817. And of course, this was accompanied by a host of electromagnetic counterparts across the whole spectrum. And then towards the end of our previous observing run, 03, we had the first detection of 2 neutron star black hole binaries in short order within about 10 days of each other. And so you can really see that the improvement in sensitivity between 03 and 04 has led to a dramatic increase in the rate at which we are detecting gravitational waves. So this is happening a couple times a week now. And this plot is honestly probably already out of date because I think I downloaded it at some point last week and we've detected a few more since then. So this 369 number is probably higher at this stage. Okay, so we can take a look at all of these gravitational wave events. It wouldn't be a LIGO Virgo Kagra talk if I didn't show this masses in the stellar graveyard plot. So the x-axis carries absolutely no information. It just looks nice. And so in blue are our black holes that we've detected in gravitational waves. In orange are the neutron stars. And then in pink and yellow are the electromagnetically detected black holes and neutron stars. And so we can already begin to see some interesting trends here. Seems like in general, the black holes that we are detecting in gravitational waves tend to be more massive than those that have been detected electromagnetically, although I think this guy is Gaia black hole 3, and so the observation of a 30 solar mass black hole in our own galaxy is pretty cool. But we're not going to talk about the masses at this workshop. We're going to talk about the spins. And so while it's nice to look at all of our gravitational wave events individually, we also want to consider the population as a whole. So I'm going to very briefly tell you how we go from The measurements of our gravitational wave strain as a function of time, you can see here the data from the very first event to some measurement of the parameters of an individual event. So these are the posterior probability distributions for the masses of that first event, GW 150914. And then once we've characterized our whole catalog in terms of, in this case, masses, but we'll do the same for spins, we can turn this into a population level measurement in order to extract that astrophysics that I mentioned was encoded in the population properties earlier on. And so the first step is actually detecting gravitational waves, and we do this using a technique called match filtering. Basically, how this works is you take this gravitational wave strain data and you're constantly comparing it to the gravitational wave signals that are expected theoretically across the parameter space of interest that live in some pre-computed template bank. And you're trying to maximize the match between a given template in your bank and the data. And if this match exceeds some detection threshold, you say, I've detected a gravitational wave candidate. So the best matching template gives us a point estimate for the parameters of the binary, including the components of the spin aligned with the orbital angular momentum. But we don't just want a point estimate for the parameters of the binary, we want a probabilistic representation. And so the next step is to use Bayesian inference to sample across the whole 15 for binary black holes and 17 for binary neutron stars, dimensional parameter space in order to obtain posterior probability distributions. And in the LDK collaboration, this is often done with a software called Bilby, of which I'm one of the developers. Okay, so what are the parameters that we are actually trying to measure when we do this? So each of the objects in the binary has a mass and a three-dimensional spin vector that's parameterized in terms of a spin magnitude chi from 0 to 1, spin tilt with respect to the orbital angular momentum, and then I also mentioned this as an equal spin angle. But as I will show later, we do not measure any of those spin parameters particularly well. And so instead, we often talk about these effective spin parameters that have a bigger impact on the waveform, and so we can constrain them better. And so the first is the effective aligned spin. This is the best measured spin parameter that we can probe with gravitational waves. It is the mass-weighted spin aligned with the orbital angular momentum. And then on the other hand, we have the effective precessing spin, which is just the mass-weighted spin projection onto the orbital plane. And so these are lossy parameters. So chi effective of 0, you can have this either if the spins are oriented exactly in the orbital plane or if the spin magnitudes are 0. But as you'll see, we measure this parameter much better than any of the component spins. And so we are trying to do astrophysics with this, even though it's a complicated function of many different quantities. Okay, so how do we actually get the spin from the gravitational wave signal that we observe? So we have deterministic predictions for what the gravitational wave signal should look like from general relativity. These are these waveforms, which are shown in terms of strain as a function of time. So of course, the amplitude and the frequency, both in general, increase as you get closer to merger. So for systems that have a higher spin aligned to the orbital angular momentum, they will take longer to merge at the same value of all the other binary parameters due to the orbital hang-up effect. And so you can see here basically what this looks like. In blue is a non-spinning waveform, and then in green is the waveform of our spin, a system with high aligned spin. And you can see that this just takes longer to merge. And so this is one way that the aligned spins are encoded onto the waveform. And for the precessing spins, if the system has tilts that are misaligned with respect to the orbital angular momentum, they will exhibit spin precession. And this can be observable as a modulation in the amplitude of the waveform, which you can see here in the green waveform. In the most extreme case, you can think about this if you were seeing the binary edge on, the orbital plane is wobbling because of the spin precession. And so sometimes you see the top and sometimes you see the bottom. And this is how you end up with these amplitude modulations in the waveform. And so this is roughly just to give you some physical intuition for where the information on spins actually comes from in the signals that we observe. So let's take a look at our 150 odd gravitational wave events and see what their spins look like. So these are the spin magnitudes of all of the events in our fourth gravitational wave catalog, both the primary spin, so the spin of the more massive black hole, and the secondary spin, which is the spin of the less massive black hole. And basically, the biggest takeaway from looking at this plot is that the uncertainties are large. And so for many of these events, we can barely constrain the spin somewhere between 0 and 1. There are a few exceptions where we can make a more powerful measurement. For example, in this case, we can measure that both objects are confidently spinning, but for the most part, we don't measure this very well. Okay, so looking at the individual events, we're not learning a lot. But there is one interesting event that I want to highlight. So earlier this summer, the LVK collaboration announced the discovery of GW231123, which is both the most massive and probably the spinningest binary black hole merger that we have observed to date. And so here you can see the estimates of this binary's masses. They are both likely over 100 solar masses, which is pretty weird because we think that we shouldn't be able to form stellar mass black holes with masses in this range. And so at least the merger of this object is definitely an intermediate mass black hole. And then the spins are also exceptionally high. So here, there are different blobs on these corner plots because of different waveform models. But regardless of the waveform model, you see that at least the primary spin is constrained to be almost maximal. And so this is weird. We don't quite understand how this system formed. It could be one of these hierarchical mergers, but we think actually the spins are too high for it to be hierarchical. And so, yeah, we hope we detect more of these weird high spin, high mass events in order to hopefully better understand where they're coming from. Okay, so I mentioned that we want to look at the population. And so to do this, we use a technique called hierarchical Bayesian inference. Basically, how this works is I've now plotted all the posteriors on chi1 and chi2 that I had showed you on the previous plot. Again, looking at this isn't very informative. You think maybe there's more probability at low spins, but most of these measurements are quite broad. There are a few clearly high spin events, including GW231123. And so what we're going to do is that we're going to assume that all of these events are drawn from some overarching distribution. In this case, we're going to model the spin magnitudes as a truncated Gaussian. And then we basically want to see what are the mean and width of this truncated Gaussian that best fit the data. So we want to decide basically which one of these dashed white lines offers the best overall fit to the population. And when we do this, we can self-consistently account for our statistical uncertainties. So we take into account the fact that we don't measure the spins of any one event very well. And we can also take into account observational selection effects. So because we have this deterministic prediction for what the gravitational wave signal should look like from general relativity, we actually know exactly how sensitive we are to a given source, and we can account for that. And so all of the population level measurements that I'm going to show you are the underlying astrophysical distributions of black holes in binaries that end up merging within the age of the universe. They have already removed our gravitational wave detector sensitivity from the picture. Okay, so without further ado, this is our population level constraint on the distribution of black hole spin magnitudes. And you can see that they are small. So we have much more posterior support down at small spins than we do at high spins. There are two different models here. One is this truncated Gaussian model that I mentioned in orange, and then there's also a more flexible model using splines in purple. So many of the plots that I'm going to show will have multiple models. In general, one imposes a stronger functional form than the other, which is more data-driven and flexible. And so the fact that we find that black hole spin magnitudes are generally small is consistent with this picture of efficient angular momentum transport in the stellar progenitors of these objects. But we're also interested if some of these systems have vanishingly small spins. So we find that they're small. This distribution peaks at around 0.2, but is there some subpopulation of binary black holes that have spins that are exactly zero? And basically, we're now going to change our model and allow for a spike in the distribution at zero, and we want to measure the fraction of sources that are in this spike. So there was a lot of debate about this with the data from our last catalog in GWTC3. The general consensus was that it was possible that up to 80% of sources had exactly zero spin, which big if true. So now with GWTC4, we have more than doubled the size of the catalog, and we get a much, much stronger constraint. We find that no more than 35% of systems may have one or two negligibly small spin components, and this is the posterior on the fraction of sources in this spike. You can see that it peaks quite strongly at zero. And so this was a case of more data made the picture clearer, and so we are finding that probably black holes in binaries with other black holes don't actually have zero spin. They have some small but non-zeros. Okay, so far I've been talking about the spins of the more and less massive black holes, but especially if we want to compare with the spins of stellar mass black holes and X-ray binaries, probably a better question to ask is, what is the spin of the more rapidly spinning black hole in each binary? And so this is a method that I developed a couple of years ago where we're going to sort the components of the binary by their spin instead of their mass. And when we do this, you can see here the population level distributions of chi A, the spin of the more rapidly spinning black hole, and chi B, the spin of the more slowly spinning black hole. And you'll see that chi A peaks away from zero and peaks around 0.3 or 0.4, while chi B is consistent with peaking at zero. And so this is possibly a hint of that tidal spin-up mechanism where one of the black holes in each binary has a considerably higher spin than the other. And with an undergraduate student at Princeton, we wanted to compare our measurement of these spin-sorted spins in real data to what we would get from a simulation, basically to be able to say, is this inconsistent with this picture of both black holes have zero spin? And so when you analyze a fully non-spinning simulated population, these are the population level distributions of chi A and chi B that you get. You can see they're quite different and much more strongly peaked at zero than the real data. And so again, this is just another way of saying that not all black holes have negligible spin. Okay, and so instead of saving all my open questions for the end, I'm gonna kind of intersperse them throughout the talk. And so I think one of the things that I'm very curious about is, now that we have a clearer picture of what the binary black hole spin magnitude distribution is, where is the spin actually coming from? Is it a natal spin? Is it a tidal spin up? Is it spin up from accretion? Is it from hierarchical mergers? And how can we actually distinguish this based on our gravitational wave observations? Do we look for subpopulations? Are there correlations imprinted between the spin magnitudes and the other binary parameters that would allow us to distinguish these different ways that these black holes might have spin? All right, so I'm going to move on to the spin tilts. Here they are for, again, all of the events in GWTC4. Again, you can see that we do not measure the cosine of the spin tilt angle particularly well. But there are a few events that seem to prefer to be either exactly aligned or anti-aligned. But if you look at these events individually, there's no clear evidence for deviation from isotropy. This might be an isotropic distribution. And so we need to wield our hierarchical Bayesian inference hammer in order to look at the population as a whole. And so these are, again, with two different models, the population level distribution of the cosine of the spin tilt. So -1 is fully anti-aligned and 1 is fully aligned. And so new in our analysis of the GWTC4 data is the possibility that this distribution peaks somewhere other than exactly aligned. So I mentioned earlier on that we expect that binaries that form in isolation should have mostly aligned spins. And so all of our previous analyses built in this assumption, and you can see here in the dashed white lines, this was our result of the inference from the previous catalog because we assumed that this distribution would peak at 1. And so in this latest analysis, we relaxed this assumption And lo and behold, the distribution does not seem to peak at 1. It seems to peak at a cosine of like 0.2. There is no good astrophysical reason for this, so this is really weird. If there are theorists in the room who have some good explanation for why they should be a preference for spin tilts to peak at around 75 degrees, I would love to hear it. But this is weird. However, one key takeaway that we can glean from this plot is that there is significant evidence for some fraction of systems to have cosine tilts that are negative. So the fact that we have evidence for systems with cosine tilt being negative tells us that some fraction of binaries are forming dynamically, because we think in the canonical picture of this isolated evolution channel that it's difficult for binaries that form via that channel to end up with tilts greater than 90 degrees. That would be negative on this plot. So I think for tilts, the question in my mind is, are they really a reliable tracer of the formation channel? So for a long time, people were saying, this is how we're going to distinguish formation channels, because dynamical binaries will have an isotropic distribution and field binaries will have a distribution that peaks at aligned spins. And this was going to be our holy grail. We would just measure the fraction of things that had an isotropic tilt distribution, and that would be exactly the fraction of sources that form dynamically. I think this feature is telling us that that picture is not as clear as we thought and hoped it would be. And so, there are all of these theories for spin axis tossing, and we're kind of always assuming that the black holes inherit the spin direction of their progenitor stars. And so can we actually find a more realistic model on the astrophysics side that will allow us to actually make this a more robust tracer of formation channel? Okay. Right. So we had a question about chi effective. This is another slice along our spin parameter space that we can look at. So you can see here that chi effective is clearly much better measured than the component tilts and magnitudes. There are a handful of events that have confidently positive chi effective, although no individual events with confidently negative chi effective, but many events could have negative chi effective. And so when we look at the population level distribution, we can see that more binaries are aligned with positive chi effective than anti-aligned with negative chi effective. So mu in GWTC4, we fit the population level distribution of chi effective with a distribution that is allowed to be skewed. And we actually find significant evidence for the skewness. So this is the posterior on the degree of skewness. 0 means no skewness. And so it's basically going back to our previous model, which was just a Gaussian. I think there was a question. Okay, but yeah, basically we can measure the deviation of this inferred distribution away from something that is symmetric about chi effective of 0, which is what we would expect for a dynamical population. And we can turn that into a fraction of sources that form dynamically. And so we find that at most 84% of binaries come from an isotropic distribution of spin tilts, and turn that into a constraint on the dynamical subpopulation at your own risk. Okay, so there's one other spin parameter that I want to measure, which is this azimuthal spin angle between the in-plane projections of the two spins. This parameter phi12 is interesting because it is a tracer of a dynamical effect called a spin orbit resonance. And this is a signature of isolated binary evolution, and also can help us distinguish the birth order of the black holes in the binary. So for objects that form under the standard mass ratio scenario, where the more massive star becomes the more massive black hole, they will preferentially be drawn to phi12 equals plus and minus pi, so anti-alignment in the azimuthal spin angle, while those that undergo mass ratio reversal, so where the more massive star becomes the less massive black hole because of mass transfer in the binary, those will be drawn to phi12 equals 0. And so whether a particular binary is caught in one of these librating morphologies where phi-1,2 kind of sticks around either aligned or anti-aligned. Depends on the spin magnitudes, the tilts, and the mass ratio. So not all binaries will end up in one of these librating spin morphologies. Many of them will just be freely circulating and freely processing. But if we can measure the fraction of the population that is in one of these special configurations, we can again use that to learn about the formation scenario. Unfortunately, this parameter is even more poorly measured than the spin magnitudes and the spin tilts. And you can see here the width of the 90% credible interval for the posterior on this parameter as a function of total mass for a variety of different simulated systems. So even for a signal-to-noise ratio of 60, we do not measure this parameter well. The dashed white line is basically the 90% confidence interval of the prior for this parameter. And so extracting information from this is going to be tough. But in work led by Vijay Varma a couple years ago, we actually showed that if you measure this parameter at a reference frequency closer to merger, so again, because of precession, the exact value of this parameter as a function of the gravitational wave frequency will change. If you measure it closer to merger, the parameter leaves a stronger imprint on the waveform, and so you can get a better constraint. And so in recent work, I looked for these features and evidence of spin orbit resonances in GWTC3. The GWTC4 updated constraint is coming soon. And you can see that there's no particularly significant evidence for spin orbit resonances in GWTC3. The distribution that we infer for this phi-1,2 parameter is completely consistent with being flat. But if these features were in the data, I showed with some simulations that we would be able to measure it in GWTC4 if there was a prominent fraction of the population that had these special spin configurations, if perhaps that feature was not so prominent, and if it was mixed with an isotropic component. So if it's in the data, we should be able to tease it out on a population level if we are patient enough and wait for a big catalog. But to me, the open question here is, are our waveform models actually robust enough in order to be able to reliably measure this parameter? So probably the most advanced waveform model that we have, which is a numerical relativity surrogate, does this well, but many of the other phenomenological models are just not encoding this information in a reliable enough way that we should really trust the measurements that we get on this parameter. And so maybe we should analyze just the subset of the population that we are confident in this measurement just to be safe. But then doing this in a way that is statistically consistent becomes difficult. Okay, and so finally, I want to mention correlations in the spins with the other binary parameters. And so one way that we tend to look for correlations is to see whether the distribution of chi effective evolves with the mass or the redshift. And so in work from a couple years ago in GWTC3, we found that the binary black hole chi effective distribution likely broadens with redshift. And so here you can see slices of the chi effective distribution that we infer at different redshifts. The brightest green color is the closest redshift, C of 0.001. And then the brown band is the farthest redshift, that is Z of 1.8, which was at the time basically the farthest redshift where we still had some posterior support for there being an object, an individual object at that redshift. And you can see that these bands are getting broader and broader. And we think that this is a signature that black holes were born with larger spin in the cosmic past. Now, we can look for this correlation with a more flexible model. So before, I was assuming a linear correlation, but we can use one of these more flexible spline models. And so in work led by MIT grad student Jack Heisel, we showed that there is still evidence for this broadening of the spin distribution when we look for the correlation with one of these more flexible models. And this is now the GWTC4 data. And so you can see that the width of the chi effective distribution really is changing as a function of redshift. You cannot draw a flat line through here. Now, the other flagship correlation that there had been evidence for in GWTC3 was an evidence for an anti-correlation between the mass ratio and the mean of the effective spin distribution. So with GWTC4 data, this particular correlation is no longer super strongly significant. You can see what this looks like here. So basically this means that more equal mass ratio systems would have smaller chi-effective, and more unequal mass ratio systems would have larger chi-effective. However, with GWTC4, we do find strong evidence for a correlation with either the mean or the width of the chi-effective distribution with redshift. We just can't really tell which. And so with the particular models that we've used to look for this correlation are clearly not exactly capturing what's happening in the data, but there's some kind of correlation there. We just can't really tell what it is. And so do these correlations actually indicate a single physical process that is leading to these features, or is it just multiple subpopulations on top of each other that are conspiring to produce a correlation that looks like the kind that we are looking for? And, what is the optimal model to choose to look for these kinds of correlations? Do we trust the very prescriptive parametric models to be flexible enough to capture the correlation, and are the flexible models that we are using actually interpretable enough that we can learn something from them? And then my very last point is that we also have a handful of black holes merging with neutron stars, so we can look at their spins too. It seems like the black holes that are paired with neutron stars are likely more slowly spinning than those that are paired with black holes. So we only have a handful of these systems, so our error bars on our population level measurement are even larger than they are for the binary black hole case. But you can see here that this distribution prefers to peak at a spin of 0. And so this would be indicative that the black holes that end up paired with neutron stars are likely evolving from different stellar progenitors than those that end up paired with black holes. There are also pretty significant differences in the mass distribution that further enforce this picture. And so what I find tantalizing is, at least in terms of the mass distribution of the black holes paired with neutron stars, those are much more similar to the masses of the black holes in high mass X-ray binaries. And so are these two populations perhaps more closely connected to each other than binary black holes and high mass X-ray binaries? I think if you evolve Cygnus X1 forward in time, the latest picture is that it might end up as a neutron star black hole merger. And so when we're talking about comparing the spins of stellar mass black holes in X-rays versus gravitational waves, should we really be looking at the spins of the black holes that are paired with neutron stars and not at the spins of black holes that are paired with other black holes? Okay, and with that, I think I'm out of time. So I will just leave up my summary slide and see if there are any questions. Thanks.
So if Silvia was the token, gravitational waves person, I am the token EHT person, at least for today. And this is going to be quite a different talk with a kind of different focus and different level of data that I am confident in presenting and saying, yes, we got rid of the insertion piece correctly. So this is a very kind of aspirational talk. Black hole imaging at event horizon scales is incredibly different compared to gravitational wave observations. Gravitational wave observations are really a precise science. And black hole imaging is also a precise science, but it's not precise necessarily in the context of GR and measuring properties of the space-time so much as it is in measuring properties of the astrophysics and the accretion and the gas and the plasma dynamics. So, okay. So as a rough outline for where we will be going, what I'll be talking about, I'm going to try and give everyone a primer on how to understand event horizon scale black hole images, kind of what goes into the geometry of a black hole image. And then I'll talk about light echoes and what I call black hole glimmer, unrelated to the computer issue that we had when I was screening. And then I'll talk about observational measurement strategies to try and extract these light echoes, again, with the understanding that all of this is kind of next generation stuff that we would be doing as opposed to, current generation stuff. And then I'll briefly have a slide on a few questions and a few of the directions that I think are the next steps in this business. Okay, as I said, I'm going to start with black hole images at the event horizon scale. So this is broadly the picture that you should have in mind. You may have seen this before. This is an image of the black hole, the supermassive black hole at the center of the galaxy M87. The primary features that you should be picking out in this is that there's a ring of light, by which I mean there's a dark thing in the middle. The ring is brighter on one side, and then there's this kind of swirly pattern that's superposed on top of the image, and that swirly pattern has to do with the polarization of the light. In other words, what orientation is the electric field oscillating when it reaches the antennas that we're using, in our telescopes to measure this. I'm not going to talk about polarization. Tomorrow, Daniel Palumbo is going to be kind of giving part 2 of this discussion of horizon scale imaging, and he'll briefly, or maybe briefly, maybe in depth, briefly talk about polarization. So I'm not going to talk about that. I think there are a whole bunch of really interesting things to do with polarization and spin connection, but again, okay, so if you're not familiar with how we make this kind of image, the way that we do this is with very long baseline interferometry. This image is incredibly small. It's on the order of 40 microarcseconds, which is about the width of an atom. If you stick your arm out, and imagine an atom at the side. It's also about the size of a donut on the moon, or about the width of a human hair on the International Space Station. So whichever one of these analogies resonates with you, please feel free to get with that. But again, as I said, this kind of process or this study is incredibly different compared to gravitational waves. Gravitational waves, GR, is good enough, as Silvia said. And so we really understand, if we see a waveform, we really understand what's in that. When we see this image, we know what the components of the image are. We know what physics goes into producing this image, but there's a whole bunch of uncertainties that make the exact blobby structure quite complicated. This image is also in a very different regime compared to the gravitational wave, very different regime of black hole compared to the gravitational wave. Waves that are produced by the black holes that we see, for example, in LIGO. This is a supermassive black hole, so this one is on the order of 1 billion solar masses. We also have another image of the black hole at the center of our galaxy, which is on the order of 1 million solar. So these are incredibly massive objects. But one thing that's maybe kind of nice about these objects, in contrast to the LIGO stuff and the gravitational wave stuff, is that these are really black holes in isolation. So instead of trying to measure what the spins of black holes are or the properties of the black holes are when they're in binaries, we're just looking at a single black hole. So if we can measure the spin here, this is kind of we're probing a different category of black hole, these supermassive black holes, and we're also probing it in a different way, not a dynamical measurement, but a measurement of black hole dissipation. And so for the rest of this talk, the philosophy word that I want you to have in mind is consilience, which effectively means, I think that so consilience means taking a measurement or coming at data from 2 different approaches. And so the way that I think of measuring spin or trying to get constraints on spin from horizon scale images is that, maybe we have access to 2 black holes in the entire universe where we can do this, or maybe at best 10 where we can do this. This is a huge contrast compared to the 150, binary events that we might have from gravitational waves so far. But if we can somehow access systems or get some kind of constraints on spin from these horizon scale or near horizon scale measurements, and then contrast them with measurements from gravitational waves in some way, or from X-rays or whatever, that'll really help us build a better understanding of the systems overall. And so that's the picture that I want you to have in mind. Okay, so very briefly, what goes into producing such an image? Well, we made this image with the Event Horizon Telescope, which is an interferometer. I have 2 slides on this. I think it's worthwhile to kind of have this in your mind, but it's not important so much for the rest of the talk. The way that interferometers work is you have telescopes at different locations, for example, on the planet, very far spread away, and they're looking at the same source, and they see slightly different signals. And by contrasting what we observe at telescope A versus at telescope B, we learn something about the spatial structure of the source in a particular direction. So if we have a telescope down in Chile and another one in Spain, then we learn something about the image. We learn something about structure in the image and the source that these 2 telescopes are observing along this orientation here. And in fact, the way interferometers work is they're measuring complex amplitudes or complex visibilities in the Fourier So it's the Fourier transform of the image. And the great thing about, well, one of the great things about the Earth is that it turns. And so over time, as the Earth turns, the orientation of this track changes, and then different telescopes start to be able to see the source. And so we really end up sampling a bunch of the Fourier plane, and so we get a whole bunch more information about the Fourier transform of the image. And then over time, we can kind of build out our understanding geometrically of what we see. This is an animation that was compiled by some combination of Michael Johnson and again, Daniel Palumbo, who's sitting in the audience. So you can ask him about it if you'd like. I'm going to play this animation again, but now I'm going to add a different panel on the right, showing you what we construct in the image at all of these different times. So if we just have the single snapshot with just the information along this one direction, then we really don't get that much information about what the image is. We just get information along a single direction. But again, as the Earth turns, we get more and more information about different orientations in the image. And over time, we construct a more faithful representation of what's actually in the sky. You will notice that this image is blurry. It's an incredibly high resolution image because, again, we're looking at atoms at a meter length, but we only have a few resolution elements across this image. And so this is a theme that's going to come back time and again. We don't really have that much data. And so if you want to do a precision measurement, spin measurement, that's okay. But anyway, this is the image. This is how we produce it. So what are we actually looking at here? I've made the point that black hole imaging is very closely related to questions of astrophysics or astrophysical dynamics. So I want to briefly give you a tour of the accretion system. So we are in particular considering low luminosity sources, low luminosity accretion disks. And this is a particular class of accretion disk. And again, I'm just going to emphasize this point that unlike with gravitational waves, what we are doing is we're not measuring something in our image that is directly produced by the black hole, gravitational waves being directly produced by the black hole. Instead, we are measuring something that is near we have this hot gas, this hot plasma in the order of 10 billion, 100 billion Kelvin that's falling toward the black hole and onto the event horizon. And we're looking at that plasma. So this is already one step removed from the black hole itself. Black hole accretion is incredibly complicated and has many astrophysical uncertainties. And the systems that we're looking at with the EHT, those two sources, the supermassive black hole in our galaxy and the supermassive black hole in the nearby galaxy M87, are low luminosity and radiatively efficient, which means that we typically believe that the accretion disks are geometrically thick and optically thin. And so here on the left, this is kind of the image you should have in your mind for what the accretion disk looks like. So I will gesticulate now. We have the black hole and some disk of matter that's swirling around like this. And on the top, I'm showing you a slice through this plane. And in the bottom, I'm showing you a slice through the midplane, again, showing you the log of density in both cases. And so this is really, a complicated thing. There's a bunch of turbulence, a bunch of variability going on. There are sometimes completely evacuated regions that open up. And this is what we are looking at in the image. And this is how, this is what we ultimately want to try and extract a spin constraint from. It's not the black. One point that has been brought up before is, do we care about the mass of the disk compared to the mass of the black hole? And for these systems, the answer is an unequivocal absolutely not. The mass of the disk within, let's say, 50 to 100 gravitational radii, black hole, is often on the order of 1 billion times less than the mass of the black hole itself. So it really, really doesn't contribute. So this is a hard problem, right? We're looking at this gas that's doing a whole bunch of complicated plasma fluid things and trying to extract spin from it. So, the same black hole spinning in the exact same way can produce incredibly different emission morphologies. Here's some examples of that. I'm taking the exact same relatively high spin black hole here, something like this, and I'm changing the plasma physics parameters. And we can talk about that if you are interested, but I'm not going to talk about it now. I'm just changing the plasma physics parameters. I'm changing the model that we use. So people in the lab, shoot lasers at little pieces of metal and measure properties and say, this is how I believe that electrons get hot. And someone else will do the exact same experiment and say, no, I don't think you're right. I think that this is how works. And so to marginalize over this uncertainty in our modeling, we have different prescriptions for how hot to make the electrons. And just choosing one of these different plasma models can significantly change kind of where the emission is coming from in this exact same flow. And so again, this is an astrophysical uncertainty, something to keep in mind. And kind of what I hope to do in the rest of the talk is convince you that even though there is this huge level of uncertainty in what's actually producing the emission and the geometry of the emission region, we can still make some headway in this spin measurement regime. So I'm gonna quickly show this. This will be the last kind of animation or graphic telling you about how black hole images work. But effectively, again, I have some disk of matter around the black hole. It's hot. It produces photons. There's a magnetic field somewhere in here. And so the magnetic field controls the direction of the light that's emitted, the orientation of the electric field. And so, again, I have this hot plasma, and this hot plasma is emitting light. And eventually it goes throughout all of space and ends up arriving on the screen. And we see some kind of ring. So this is the picture you should have in your mind. There's a hot disk of plasma that produces light, and that's what we see. So now going to a simulation, here is a high-resolution image, simulated image of a black hole. And I want to walk you through some of the geometric features here so you understand why there's this darker thing in the middle. Darker thing just corresponds to the black hole event horizon itself. And you understand why it's kind of broadly brighter in this ring feature. There's just some hot gas. But you will notice that there's this kind of brighter part around it. And it's worth understanding exactly what's going on there. So what I'm going to do for that is I'm going to look at a horizontal slice in this image. And I'm going to set up a camera at this horizontal slice and ask every single photon that I receive at this point, or this point, or this point, or anywhere along this cyan line, where did it come from in this? So I'm going to ray trace backward into the image plane, or toward the image. So I'm setting up my camera over here, and I'm just going to shoot back all of the trajectories, or follow back all the trajectories of the light. And it looks like this. And completely unsurprisingly, if you have a photon trajectory that goes close to the black hole, it feels the influence of gravity much more. And whereas if you're further away, the curvature will be less. And there's this kind of critical impact parameter, a critical point along this blue line that corresponds to a trajectory that exactly straddles the regime in which the geodesics fall directly onto the black hole, compared to the regime in which the geodesics escape out to infinity. And so there's this critical impact parameter in a black hole image that kind of maps out the curvature or picks out a particular level of curvature in the space-time. And this feature here, this critical impact parameter, is going to be absolutely essential for the rest of the talk, for the rest of going to describe to you. And so I want you to think about this for a little bit, and if you're unclear, ask questions as I continue to talk. Right. So this critical impact parameter, again, differentiates between geodesics, between photon trajectories that end up intersecting with the event horizon, and those trajectories that end up escaping out to infinity. And this is a spin conference, so how does this relate to spin? Well, this marginally bound, I should say circular, unstable circular orbit for photons has a particular radius, which you will note on this screen. But the radius is controlled by the spin of the black hole. So in fact, if I have a spinning black hole, there are multiple circular orbits that a photon can follow in this black hole spacetime that depend on the spin of the black hole. And this kind of conceptually, I think, makes sense. If you have a black hole and it's spinning, and you have a photon that's going in a direction that's aligned with the spin, then it'll be pulled with the black hole spacetime as the black hole rotates. And so you can orbit around the black hole very, very close if you're orbiting in the same direction as the black hole is spinning. In contrast, if your photon is going exactly opposite the way the black hole is spinning, then you have to orbit at a farther distance. And if you are at some intermediate radius in between this prograde close-in orbit and this retrograde far-out orbit, then you get all of these really wacky and I think quite interesting trajectories. Right. And so the crucial point here is that the trajectories that are allowed, or the circular photon orbits that are allowed, depends very, very in a very detailed way on the spin of the black hole. So if the black hole is not spinning at all, there's one radius at which this can happen. And photons going in this direction versus going in this direction versus going up versus going down versus whatever don't know about the spin of the black hole. There's no preferred orientation, so they're all going to do the same thing. But as you spin up the black hole, you start to see prograde orbits and retrograde orbits and all of these intermediate orbits. So it turns out that each of these orbits maps to a different part of the image. And so the prograde orbit maps to one point on this kind of critical impact parameter. The retrograde orbit maps to a different point. And now here is a garish slide showing all of those mappings. You don't need to remember that. If you want to, you can. You don't need to remember it, though. But the point that I want you to take away is that this very, very short orbit maps to a particular point. This longer orbit maps to a different point. And so if we can in some way resolve on a black hole image or in a black hole movie, if we can resolve what's going on over here versus all the way along this set of critical impact parameters, then in some way we are getting a measurement handle on what's going on in the black hole space-time. And what you will notice is that all of these geodesics that I've drawn here, I'm not talking about the emission structure. I made the point earlier that the emission structure is very complicated and depends on plasma uncertainties, but these geodesic structures, the locations of these circular orbits, doesn't care about that at all. They just care about the geometry of the space. Right. So to make this a little bit more concrete and to remove all of the arrows, actually, what I'm going to do is I'm going to draw this critical curve, this set of critical impact parameters for a variety of different spins, and that's what I'm doing here on the left. If I have a weakly spinning black hole, or black hole that's almost not spinning at all, then that critical curve will be nearly a circle. Because again, photons that are going in one direction versus another direction, there's nothing to break the symmetry there. They're all going to do approximately the same thing. They circle. But as I spin the black hole up more and more and more, this circular feature kind of compresses on one side into the shape of something that looks kind of like a smooth letter D. Unfortunately, this is still a relatively complicated question, relatively complicated affair. What I'm showing you here is the image you would see for a black hole if you're looking edge on. Unfortunately, if you're looking straight down at the black hole, again, you've gone into a symmetric case. And so as you increase your inclination, I guess as you decrease your inclination in this convention, going all the way up to looking straight down the spin axis of the black hole. So spin axis observer misalignment of 0, you go from this D shape back to a circle. So there is some fundamental degeneracy in the shape here, corresponding to if you're looking at a slowly rotating black hole from above versus, a slowly rotating black hole from the side versus a rapidly spinning black hole. Okay. So the last kind of theoretical thing that I'll be talking about for image structure is that we can take the fact that there are these winding orbits, and we can then conceptually decompose this total image into a sequence of sub-images. And so that's what I'm doing over here on the right. We take the full image, and we can say, well, the full image comprises a sequence of sub-images, which are constructed from the photons that, for example, have undergone no winding around the black hole, so 0 winding around the black hole, plus photons that have undergone 1 turn around the backside of the black hole, plus photons that have undergone 2 turns, one around the front, back, and so on, and so on, and so on. And kind of this geometric structure will become important later on. Again, conceptually, you have a black hole image, there's a bright ring, and there's been a particularly thin bright ring used as well. All right, so time for a quick reality check. I've talked about all of this really nice, precise, detailed structure in black hole images, but we really don't have access to any of this with the data that we've seen so far, with the Event Horizon Telescope resolution data. So over here on the left, I'm showing you images that were reconstructed by the EHT over four different days in April 2017. And over here on the right, I'm showing you different simulated images blurred to the same resolution as the Event Horizon telescope instrument would produce. And, there's some variation here. And so you might think, okay, there's some interday variability. Certainly this black hole is not changing its spin over the course of, 6 days. So, there's some interday variability, but, there's also variability in the model. So you might be hopeful. In fact, these two images here correspond to a non-spinning black hole and a incredibly rapidly rotating black hole. And I don't even remember which one is not spinning and which one is, spinning rapidly. So this is a big problem, right? If you just have access to these images, it's very, very hard because of these gastrophysical uncertainties. It's very hard to figure out how quickly is this thing spinning. My day job has me working for the Event Horizon Telescope collaboration, though. So I do want to quickly give an aside that we do still learn a lot from black holes, even if we don't learn much from the spin. I'm not going to read this all to you. But the fact that there is a brightness asymmetry, the fact that the polarization is doing something, the fact that there's some relationship between the position angle of the brightness asymmetry and other features that we see, for example, jets on larger scales. These all tell us stuff. We can also look at temporal variations in the data. So the UHT does a whole bunch of really interesting astrophysics. Polarimetric data is absolutely great here. We can maybe directly observe black hole jet launching, but maybe we can't exactly measure spin from an EHT-like measurement yet. So this leads me to the second part, which is light echoes and what I've called black hole glimmer. And again, this is kind of aspirational forward looking. So here's this diagram that I showed you before. Light that's emitted at a single location, so you have some hot spots and little flash of light that's produced somewhere in the disk, can take multiple different paths to an observer. And so in my very basic cartoon up here on the right, you have photons that are produced and go up here, or go here, or go around the black hole once and reach the observer. And what this leads to, time domain, is a characteristic light echo. So even though you have one source, one flash, one source of photons, you'll see it multiple different times, with the time delay corresponding to the amount of time that it takes for a photon to make one orbit around the black hole. And what I told you before is that the time that it takes for a photon to make an orbit around the black hole depends on the spin of the black hole. And in fact, if you have rapidly spinning black holes, or if you have spinning black holes at all, then there's not just one path that the light can take. There are multiple different paths that the light can take. And so if you have a spinning black hole and you somehow get access to these characteristic light echoes, then you will measure a spectrum of echoes for a spinning black hole, where that spectrum tells you what the spin, or gives you information about what the spin of the black hole is. And so to make this a bit more concrete, again, remember that if I look at different parts in the image, I'm looking at the effects of different circular orbits that in some parts of the image corresponds to orbits that are very close to the black hole and will have a short time delay. In other parts of the image, I'm looking at things that have a long time delay. And so here's a black hole image. I made a movie of it in a very simplified ideal example or ideal case. And over time, the time delay of the signal you measure at this point in the black hole movie shows a characteristic echoing at approximately 15 GM over C cubed. But if you look in a different part of the image, there's another characteristic echoing that's at a different time delay period. And if you look at another part of the image, there's another characteristic echoing that's at yet another different time delay period. If you change the spin of the black hole, this pattern changes. So what I'm going to do is I'm going to quickly walk through, or I guess I'm going to quickly animate through these echo responses for different levels of spin for the black hole, and then also different inclination. Remember, I told you that there's some degeneracy in the shape of that critical curve with the inclination of the spin. It turns out that degeneracy is more or less broken in this echo signature. So first I'm going to go through and change the spin of the black hole. And so this echo response, the spectrum of echoes, changes as I increase the spin of the black hole. And then as I change the inclination, again, this echo response changes. Then I'm going to bring the spin back down. And so as you look at any particular black hole system with some spin and some inclination, if you somehow can get access to this echo spectrum as a function of position in the image, then you really can directly constrain both the inclination and the spin. This is a nice kind of mathematical result. You can do this all analytically. What happens if you try and do this with a slightly more realistic model? Well, the simplest thing to do there is to look at what happens if you have a hotspot. So here I take a simulation of a black hole and I flash a little hotspot, a Gaussian hotspot, very quickly. And I measure the echo response in different parts of the image. That's what these different colored lines are. So I'm measuring in different quadrants of the image. That distinction doesn't matter so much. But what you find is that as you change the spin of the central black hole with the same exact hotspot model, you can, in fact, identify, okay, this echo period is longer than this or than this. And if I look in different parts of the image, different quadrants of the image, then in fact, I do see a different echo. So this is a realistic principle, this idealized model, to measure the spin. A cute little anecdote that I like to give whenever I show the slide is that, in fact, when I was originally making this plot, I had a mistake in my labeling. And I was looking at the plots and I said, wait a minute, that doesn't look right. I bet this is a different spin. And it allowed me to find the error in my plotting script, which means I think that's very clear evidence. In fact, by looking at this, you can make a spin measure. Okay, great. So this is all fine and dandy, but this is a kind of unrealistic hotspot model. What happens if you want to make a more realistic source model with all the turbulence, with all of that uncertain plasma physics that I described earlier in the talk? And so now I'm going to go to the penultimate part, which is observational measurement strategies, and first address the question of, what time delay should we even expect to see? So if we have a hotspot, we know exactly what the time delay should be because we can trace all the geodesics that are going from the hotspot to the observer. But in a realistic accretion flow with all of the plasma turbulence and so on, what time delay should we see? So what I'm showing you over here is, again, a slice in this direction for the black hole accretion system. And the colors are showing you where the emission is produced, given a particular model for the emission, given a particular choice for the plasma physics. And then the overlaid contours are showing you the time delay that you would expect to see. So for example, emission that's produced here, you would expect to see a time delay of 15 GM over C cubed. For something that's produced over here, you would expect to see it at a time delay of approximately 20. And so this gives you a sense for the fact, yes, we should see some echoes in our light curves or what have you at these time delays. That's good. Can we actually do anything with this? Well, now I'm going to take a simulated light curve of a particular accretion simulation. And for now, just look at this dashed line on the top. I'm going to take a simulated light curve. I've made the case to you that there should be echoes in this light curve. So maybe a thing to do would be to take the light curve and just correlate it with itself, do an autocorrelation, and look for a secondary peak where at approximately 10 to 15 to 20 m time delay. And that's what you're seeing up here in the dashed line. And characteristically, there is no clear peak, at least no clear peak that I can see, which is disappointing, but perhaps not unexpected, given that accretion is messy, the astrophysics is messy. But of course, we know that the echoes should be there somewhere. They're a property of the spacetime. So what happens now if we take this light curve and we break it up into those constituent components corresponding to the photons that directly go from emission to the camera versus indirectly, once go around the black hole or twice go around the black hole. And so that's what I'm showing you here in this blue, red, and green curve. I'm showing you the light curve corresponding to photons that are direct versus singly indirect versus doubly indirect. And to guide your eye, look at, for example, perhaps this peak. This peak does in fact shift over to the right as we look at increasingly delayed photons that went around the black hole. And then you can look at the correlations between the blue and the red or the blue and the green, et cetera. And if you look at those correlations, you can in fact see some characteristic peak at approximately 10 to 15 or twice that if we're going from 0 to 2. So the name of the game then is that we want to somehow observationally be able to distinguish between the contributions from every single different photon, which of course is hard because if you receive a photon at your detector, you can't ask it how many times it went around the black. But it turns out that the way that the EHT works happens to be very well aligned with exactly this question of differentiating between the signal that comes in the direct image versus the indirect image. So toward the beginning of this talk, I said that, the full image can be decomposed into all these sub-images. And in fact, the way the EHT works is that it is an interferometer. So it's measuring the Fourier transform of the image. It's not measuring the image itself. And so what happens if we take this total image and take the Fourier transform of it? Well, we get something that looks like this. Here, if you care, I'm plotting the overall amplitude. Thanks. Right here, I'm plotting the overall amplitude, so I'm suppressing the phase if you want. But then I also show the Fourier transforms of all of the subimages. And so for every single subimage, you will notice that as you go to increasingly higher order subimages, that increases the level of order in the Fourier transform. And this makes sense if you think about Fourier transforms. The subimages are narrower and narrower in image space, and the narrower the feature that you have in image space when you take a Fourier transform of this, the more power that you get at long base. Those small scale features correspond to larger amplitudes in the Fourier plane at larger baselines. And so this is the first time I've used magic move in a presentation, so I'm glad that it worked. And so what we can then do is I'm going to take a slice through the total Fourier transform, again, just horizontally, and plot kind of what this signal looks like. And what I'm doing here is I'm shading the signal, showing what it looks like over time. And so the signal in the direct, the signal from the direct image in the Fourier plane has this blue structure that's very, very wide and very, 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 very variable. That I chose there, but that is quite variable. But then when you go to the higher order images, because they're geometrically confined, and because they're geometrically confined and can't move around so much, the signal ends up becoming more and more kind of confined to a particular region in the Fourier. And so even though if you're looking at large scale image features at zero baseline, even though you're dominated by the direct image, when you go to longer baselines, you start to see the indirect image. And so the idea, magic move again, is to try and correlate the light curve you get at short baselines with the light curve that you are measuring at longer baselines. Because at longer baselines, you expect that your signal is more dominated by this indirect emission, and also more dominated by the indirect emission, and also that the temporal variability more closely correlates the indirect emission. And so if you do that, this is the last, I think, complicated thought that I will show. If you do that, then you do end up seeing an echo peak. So let me walk you through this very quickly. Suppose that I correlate the time series that I get of the visibility amplitude that I'm measuring from my interferometer, that I'm measuring from the EHT. I correlate the time series at zero baseline with the time series at baseline length at 20. Then this is what I see. So I see that there's a strong correlation at zero time delay, and as I go to longer and longer time delay, I'm not really correlating. But alternatively, if I go up to 50, I say, okay, I want to correlate the time series here with the time series of the total visibility amplitude I'm measuring over here, then I'm strongly correlated at zero time delay, which makes sense. There are astrophysical correlations. But then when I get out to a time delay of approximately 10, I see another echo peak, another correlation peak. And this is directly measuring the fact that there's some signal in the direct image, there's some signal in the indirect image, it's delayed by some amount of time. And so if I look at slices through this correlation plot at different baseline lengths, that's what I'm seeing over here. This gray band is showing where I would expect the echoes to be, and then the traces are showing the actual thing that I measure. For what it's worth, these baseline lengths are more than what is accessible to the current EHT on the ground, but it's maybe possible if you put a satellite into medium orbit or you go. So again, as I said, all of this is quite aspirational. We can't exactly, or we don't know how to do this yet with EHT, but it might be something we can do in the future. I'm going to skip this slide and just go through my next steps. So I think there are a lot of next steps. I've hopefully, given given you some excitement about the possibility of measuring echoes, but I've also hopefully impressed on you that this is accomplished. So things that I haven't talked about are the fact that this echo feature, again, because it corresponds to geometric photon orbits that don't really care about the emission, this echo feature should be achromatic. So if you measure at one frequency and then you measure at another frequency and another frequency, you should see the same echo. So that's a good way to confirm that you're looking at a feature of space-time as opposed to of the astrophysics. But there are questions. What is the actual required resolution if you want to do this with very long baseline interferometry? Do you need to put something into space? Do you need to go up to a terahertz in your observations? And then what is the time cadence? So I've been talking about things in units of GM over C cubed. 1 GM over C cubed for M87 is about 9 hours. 1 GM over C cubed for the galactic center is about 20 seconds. So if you multiply that by 10, that tells you the characteristic echo delay period. You need to be measuring things with a resolution of smaller than that, ideally. So 20 seconds times 10 or 8.5, 9 hours times 10. So, these are questions that I can give rough answers to, but if you want to know the precise answers to them, you have to study. What can we learn about the astrophysics? And alternatively, what do we need to learn about the astrophysics? I've argued that, the geometry of these photon orbits is determined by the space-time and doesn't care about the astrophysics. And I think that's true, but still we are seeing light that's produced by the plasma. And so what do we actually need to learn? If there's no light being produced close to the black hole, then you're probably not going to see this. There is light being produced close to it. Obviously, there are these limiting cases. So we have to understand kind of where the boundaries are there and where we lie on that spectrum. What does it mean to realistically differentiate between inclination and spin? Not going to talk about that, but question. Can we test general relativity? Do we need to test general relativity? I think in general, testing general relativity is great. Should we do it with echoes? I don't think so. What determines the accretion flow structure and the plasma properties? Are there other ways to get at this, marginalize out this uncertainty? And as I kind of alluded to at the beginning, in principle, the EHT can see two different sources. It can see the galactic center black hole and it can see the M87 black hole. Is that enough? And if we go into space, can we get more sources? Ideally, we want to do some kind of black hole demographics thing. Can we do that? What is required to do that? And then again, this question of consilience, can we get access to a source where we can measure the spin in two different ways and then start calibrating our uncertainties? Okay, so my last slide is just a summary. Black hole images, again, are quite different compared to gravitational waves as probes of space-time. Strong lensing, however, enables light to take multiple orbits around the black hole, and this produces a position-dependent echo signature that encodes the spin and the inclination of the black hole. And although direct measurement of echoes is hard, it may be possible to detect them with interferometry, but we still have a lot to learn. And so with that, I'll thank you for your attention.
So thanks to the organizers for inviting me to speak. I really appreciate it. We're going to go back to talking about small black holes again, but the astrophysical ones that we study electromagnetically and have been doing so for decades in a slightly more disorganized way, as you will see. And I'm going to focus on this one technique. There are several techniques for measuring spins in accreting black holes. Okay, I will briefly go over them, but the talk is focused on X-ray reflection spectroscopy. And this is essentially X-rays that reflect off the disk. And if that happens very close to the horizon of the black hole, it allows us, through the GR effects on the light that we measure, allows us to measure the spins of black holes. And this is just a representation, an artist's impression of what we're dealing with, right? We have the black holes, the masses, it was shown in the first talk, of course, they're typically around sort of 10-ish solar masses, and their companions, typically, most of these systems, the companion is low mass, not in terms of the reality in the cosmos, but in terms of what we see in our galaxy. Most of these systems have a low mass companion star. Some of them have a high mass companion star. There was some of that distinction was touched upon in the first talk, and I'll get into that a little bit. But I'm going to start with just my basically my conclusions or some takeaways that I want to try and pin down on top of your brains today. So the first is that unlike with the gravitational waves, and much like with the Event Horizon Telescope and George's talk, of course, we have a lot of noise here, right? There's an advantage in that we can see a lot of stuff and we get loads of data. These binaries are in the galaxy, they're very bright, so we get tons of data, but trying to measure the spins, right, that's one particular signal in amongst a bunch of noise. So there's astrophysics, right? And the second is we use models for this reflection process to explain the data that we see, and that's a broadband thing, right? You're not just looking at an single emission line, okay? And I'll get into this in more detail in a second, but essentially a lot of the focus of spin estimates from reflection do come from this iron emission line that appears between 6 and 7 keV, but that's not all you're seeing when you have reflection, and that's not all that's in the models. It's actually the reflection of an entire continuum that has a few key features in it. And that means that it's not just spectral resolution that we care about, okay? It's actually signal to noise. Signal to noise in your data matters significantly as well. And that's why we don't need necessarily a high resolution instrument to do this kind of modeling. But of course, both matter. And I'll get into that, explain why soon. When you're doing this process of modeling the X-ray spectrum to try and tease out the reflection part of it and therefore measure spin, we have to be led first by the data and not by our great models, because every system is very different, right? We see consistent patterns in the data, but not all these systems behave exactly the same way. And that's why the situation is quite messy. And that's why I'm describing this as a noisy signal in a different sense than, say, the LIGO measurements, where there's perhaps fewer things varying, right? And my fourth point is, I think we might be, I'm not going to speak for every community, but in our own community, we might be approaching the question slightly incorrectly, in that we're trying to measure how fast are black holes spinning, rather than asking ourselves, can we show that the black holes cannot not be spinning, right? In other words, we should be ruling out models, not trying to verify our favorite models. And then finally, this will be clearer later in the talk, but we have to make some assumptions when we do this kind of modeling about what's shining the X-rays on top of the disk. And that those photons, we say they come from a corona, from a hot gas that's around close to the horizon of the black hole, but we don't know the geometry of that, right? We know what spectrum it's producing, and we can measure its variability and get some sense of the geometry, but there's uncertainty there. And of course, the reflection spectrum that you see is going to depend on that geometry, because we're doing general relativity. So where the gas is that's shining on the disk determines the signal that you see. Okay, so here we have the masses in the stellar graveyard again. It's not the most recent one, sorry. But, it makes the point very clearly that the masses are different between these systems. The X-ray binaries that we've been studying now for decades, they're all quite low mass, and the LIGO sources are much higher mass. The other distinction is that their spins are very different, and we have almost the inverse situation. So in the LIGO sources, we've got this, seems like on average, most of the sources have low spin, but Silvia explained in the first talk that maybe a couple of them might have high spins. We have the opposite situation in X-ray binaries. We think most of them probably have pretty high spins, but there are a few cases of very low spins measured, okay? And yeah, we don't really know whether these are simply different populations, or if there's something maybe that we're missing in our measurements, or there's some biases in our measurements. And this is what we're trying to figure out. Now, hopefully by the end of this talk, you understand that situation from the point of view of the X-ray binaries. So X-ray binaries vary, right? They go into outbursts, right? You have some kind of critical mass that builds in an accretion flow. It causes a rapid rise in the accretion rate. And so these things can stay quiet for a long time and then get very bright. And they go through an entire cycle that follows a similar pattern, but not identical. And that's why you should be cautious with this picture. But in general, these systems start down here in the bottom right of this harness intensity diagram. So you just have luminosity or brightness or intensity on the y-axis and X-ray hardness. So as you go towards the right-hand side of the figure, high energy X-rays are dominating. And if you go to the left-hand side, the low energy X-rays are dominating, right? You start in the bottom right, rise up through what we call the hard state, where we see power law emission. So this corona, which produces a power law spectrum and produces a lot of high energy X-rays, which are the ones that get reflected. These are dominating the spectrum. Then typically systems go through some kind of transition between this hard spectral state to a soft spectral state. And there are intermediate states that we define that I'm not going to go into the details of that, but that's based on a combination of spectral and time variability properties. You can see labeled on the diagram the jet line. There's a point at which, jets appear on the right-hand side, they disappear as you go to the left-hand side. As you get into the soft state, the accretion disk, which is producing black body emission at a temperature around a keV or so, that varies between the sources, of course, but around a keV or so, that starts dominating the spectrum and this power law component drops away. Okay? And then you return back again to this quiet state. Now, this process can take weeks, months, sometimes even days, actually. It can also take 2 years, in some sources, and the periods of quiescence can take years to decades. There are some open questions here that we still don't have answers to. We have some answers, some indications, but we don't know for sure. We have this issue of whether the disk is truncated, and this matters for reflection measurements, okay? What I mean by that is the inner edge of the accretion disk actually at the innermost stable circular orbit of the black hole? We rely on that assumption because we're trying to measure the spin, and that radius is set by the spin. So if we're not measuring that radius, we're not measuring the spin. So we don't actually know, in a lot of these systems, we don't know this, right? We have to make some kind of assumption. It can be pulled out of doing the actual reflection modeling. I'll explain that later. We don't know what the geometry of the corona is. I mentioned that already. So in a lot of these sources, the continuum is hard to represent. In some cases, it's very simple. It's a simple power law, and we can see that quite clearly. In some cases, there's more than one component, or the spectrum's just messy. And we also have jets and winds. We have other components that can be there. And winds will produce emission lines and absorption lines of their own. Okay? And that obviously interferes, because there's going to be iron in the winds, that interferes with the reflection. So this is a general picture of what we're seeing, and then this is an example of the actual data. So this is just a diagram to show you that there's generally 3 components that we always see. Okay, and these are the ones that we have a pretty good handle on. And if you want to do a good measurement of spin with reflection, you hope that this is all you see, basically. So you have a thermal component, which is the optically thick component of the disk, right? And as I mentioned, the disk can sometimes be truncated or not dominating very close to the black hole. And we can instead be dominated by the blue component, the power law, this coronal gas that's producing high energy X-rays. And then the green is the reflected part. And here's an example of an actual reflection spectrum. This is actually RXT data, the Rossi X-ray Timing Explorer. So it's quite old data, but it's very good high signal to noise data. And it's broadband, so it captures all the components of a reflection spectrum. And the main components are these 3. So you have a iron K emission line. Let me use my mouse. Iron K emission line at between 6 and 7 kV, and it gets broadened. The red represents the broadening of a baseline reflection spectrum that's shown in gray, right? So the red is including all the relativistic effects, essentially. You have an iron K edge, which appears beyond 7 kV and also gets smeared out, and a Compton hump. That's because of high energy X-rays that get Comptonized, down scattered, basically, by colder electrons in the disk, right? So these are the 3 main components. We can also do this conversely in a time variability space. So we can do what's called reverberation mapping. I'm not going to get into the details of that, but that's one other way where we try to probe spins. We can also probe the masses of black holes with this, but you can see this is a kind of a cheeky representation of that, but you because it's not actually a binary, this data. But you can see the general shape of the spectrum looks a bit like, of this power spectrum looks a bit like the spectrum on the left-hand side. So you do have an iron line and you have a Compton hump-ish. Okay, but just focusing on the reflection, how do we measure the spins of black holes in the best possible way? Well, ideally, you want your data to look as close as possible to all the parts of the model that will allow you to constrain the spin, right? So we want to see all these parts in the data, the ion emission line, the ion K edge, and the Compton hump. And if you have a high spin black hole and you are actually looking at the ISCO very close to the spinning black hole, all these components should be smeared out. So this is a kind of like consilience, sort of, right? And then you also want, fourth part here is that you want your observations to be covering this wave band. Just as a quick example of what I'm trying to say here, I would trust this spin measurement much more than a spin measurement made with a XMM Newton spectrum that goes up to 10 keV, because it does not include the rest of the spectrum and I don't have as much consilience. Okay. There's another important point to make about forming reflection modeling in order to measure spins, and that is that, and this is kind of hard to explain, but I made it in the first slide, really. There are lots of situations where the noise that your signal of spin is buried in is just too much. There's too many moving parts, there's too many uncertainties in all your different model components, and it's hard to actually get a non-degenerate measurement of spin. This diagram kind of shows that, but the point is made about one specific model parameter, which is emissivity. All this is a profile of how much emission is coming from different parts of the disk. So higher emissivity means more of the emissions coming from very close to the black hole. Lower emissivity means it's coming from further out. And you've got 4 cases here, 4 different reflection models. The focus of this paper was on jets, reflection from jet emission, but that's not the important part. The important part is whether you have a compact irradiating source that's close to the black hole or you don't. And here you can see sort of 3 cases at high and low spin that look quite similar. And only one of these models looks very, very unique. And that's when you have a high spinning black hole, but you also have a compact irradiating source. All this means is I can hide the spin of the black hole. If I don't have a very compact irradiating source, I can have a rapidly spinning black hole, but I can't see it. Okay, so this is kind of one of the main reasons why spin measurements via this method are uncertain, and also why I'll explain this more later as well. But if you measure a low spin, that can be seen as a lower limit, really. Okay, we mentioned this issue of disk truncation. I won't go into too much detail here, but this is an example. This is actually a paper by Javier, who is also the author of the model that's used to do this analysis. And here you can see a tracking of the different properties of the accretion disk, but also the properties of the spin of the black hole via the radius. So really, I'm highlighting this top panel here. So this is just one of the parameters of the reflection model is the inner radius of the disk. The assumption here is that we have a rapidly spinning black hole, and then we see where is the emission coming from in terms of the innermost stable circular orbit. And here you probably can't see the numbers, but it's going from 4 down to 1. So not only can we see that clearly during some of these observations, we must be looking at the innermost stable circular orbit of a rapidly spinning black hole, which, by the way, is a very unique solution. Not much can produce that in the data. But we also see an evolution, right, which is additional evidence that probably we have a rapidly spinning black hole with a disk that's kind of moving close to from fairly close to right down to the ISCO. Don't worry about the other parameters for now. That's way too much to talk about. Now, that was based on RXTE data. We have more recent instruments, of course, like NuStar, is still operating, and again, has a broadband coverage, but a better energy resolution than RXTE, and pretty good signal to noise as well. So you see this pretty nice, clear reflection spectrum. This is just another source, another X-ray binary. And here, the data quality is so good that you can even flux resolve the spectral analysis. So you can chop your single observation up into different flux levels. This is a very variable source, and you can even see a clean reflection spectrum at the different fluxes, right? So in some cases, the quality of the data is good enough to even track the variability in the spectrum and get a unique measurement of spin. We also have NISO. So I mentioned that having broadband coverage is key. Having coverage of the very low energies is also very important because we have that soft disk component that pops up around 1 keV. That's usually not dominating in the hard spectral state where we see mostly the power law and the reflection, but it can still be there and it interferes with things. So having the low energy coverage matters quite a bit, and NISO is great for that. Really good sensitivity and good energy resolution as well. So we have the instruments to make these measurements quite accurately. The problem again is still with the noise. Now I'm going to mention very briefly Paul Dragas's work. I won't go into any detail since he's talking tomorrow, but his focus is a lot more on the population level. So my talk is really meant to be about the modeling and some of the details of it. But here you're looking at an actual full sample of spin measurements. As you can see, they're all skewed towards to the left-hand side, which is maximal spin. But this also shows you the different methods you can use to measure spin and what estimates we have from those. For example, continuum fitting. This just refers to modeling the soft disk component that appears at about 1 keV, which gets also distorted by the spin of the black hole by the GR effects. So you can model the distortion on the black body spectrum and get an estimate of spin that way. In some sources, in many sources actually, there's pretty good agreement, but in other sources, not so much. So we do have some conflict there. There's another method of measuring spins that's not shown on here, but which is modeling of the variability. Essentially, you can look at quasi-periodic oscillations in your X-ray signal, and that's another way to tease out an estimate of spin. Again, it's almost completely divorced from these other two methods. So again, there we see some disagreements, and I think the point here is just to stress that there are disagreements within the community based on the different modeling approaches, but measurement approaches, I mean, but also in terms of error and confirmation bias. So here's just a table to show that, to emphasize that Paul does a nice job of showing what the previous spin measurements were, and then his own work focused on only new star observations of X-ray binaries, where again, there's a slight change in the spin estimates, but they're, broadly speaking, all pretty high and remain that way, no matter who does the analysis, it seems. Okay. This is a more subtle point I want to make, which is that this is all well and good, making these spin estimates for many sources. But as I already mentioned, there's loads of complicated things going on underneath the hood, right? And one of those is that, we see this reflection signal typically during most parts of an X-ray binary outburst. So during this hard spectral state, but also the soft spectral state, where we don't have that coronal gas, we still see reflection, and it's actually pretty strong. And this plot shows that the equivalent width of the ion emission line against the hardness. So the blue points on the left-hand side are in the soft spectral state, and the yellow points are in the hard spectral state. And you can see actually that the ion emission line is pretty strong in the soft spectral state. So that component is there, but clearly the continuum is going to be quite different. And that's something that's not always captured when we do reflection modeling. And yeah, the other point here to make is that even in a single source, so I've actually pulled this from Paul's work. This is black hole spin estimates against disk inclination estimates for one particular source, and also dividing the spectral states between blue and yellow, so hard states versus soft states. And you can see here that there's clearly a correlation between these two parameters. So even in our case, it's complicated. It's hard to get a unique measurement of spin because there are dependencies there. Now, right, this I'm going to show here an example of. This is a paper that was written in only about a year ago that it tries to explore basically what could be the possible sources of uncertainty in spin, right? And I've kind of alluded to them already, but you can see here that what spin constraint you get. So that in case you can't read, the left-hand plot shows a very high spin solution to model solution. The middle one shows a sort of intermediate, and then on the right you have a low spin solution. And the point of the figure is to demonstrate that whatever assumption I make about the underlying continuum model, that's going to lead to different spin estimates. However, you have to be very careful when you do this, because this is an example of an unnecessary confirmation bias. Essentially, I can throw as many model components as I want at my total model, and then see what it does to the spin estimate. But this does very little in terms of can I rule out some models, right? It's also encouraging degeneracy. You're adding unnecessary model components in order to show that the spin can be different. I would say that we should, again, that's kind of the point I made in the first slide, we should be driven by the data first. What signals do I see in my data and do I know are there? And then model those and constrain the parameters. Models doing things in this way, I think, is a little disingenuous, in my opinion. This is another example of the same thing, right? So again, we've got different points of view on the underlying physics that's unknown, right? What we see in the spectrum is, especially in this case, can generally be represented by only a few components. We have a soft disk component, we have a power law component that's getting reflected, and you can see a really clear reflection spectrum here, right? I don't know if it's really obvious to you, but this is the relativistic reflection model. This is the actual data. And you can see an ion emission line here. You can see the Compton hump. There's a curvature there. It's not a simple power law, right? So there's clearly reflection spectrum. What we don't know is the exact underlying continuum, but the best approach to estimating that is to pick the simplest one. And that's not what's being done here. So I'll explain what the difference is between these two. So the left-hand side is basically a simpler model. It has one fewer component in the continuum. Okay, has one fewer spectral component. The right-hand side has an additional component. The left-hand plot results in a high spin, and the right-hand one results in a low spin. Now, again, this is the same process here. I would argue that what's happening here is that there's a preference to show that you can have a low spin, and you can do that. You can do that with almost any model. You can create the result that you want by adding more components because you have more degeneracy. Okay, this is an example of a source where we're fairly confident that nothing else can explain the data but a very high spin solution. This is a paper Javier and myself published a few years ago on a very high signal to noise RXTE spectrum. That's, again, it's quite broadband from a few kV up to beyond 40 kV. So you capture all these components, you capture the line, the edge, and the Compton hump. And here, what I'm demonstrating is that basically I tried my absolute best to throw every possible model I could at this data set that assumes that I have a truncated disk. So that assumes that I'm not actually able to measure the spin in this source. And so here you can see a non-truncated disk solution, and you can see in the model on the right-hand side that it's really broadened and represents the data very well. Then you truncate the disk out to 10 times that, and then 50 times that, and I just cannot make the models fit the data. So this is an example of a data set that allows me to non-degenerately constrain spin, and that's easier to do if the spin is actually high. Okay. If the spin is actually low, there are more ways for me to circumvent the reflection model. Okay. Right now, I'm going to get into just a few key areas of the modeling, like recent developments that have happened. There's some physics that has been missing in the models. Again, most of that driven by the fact that we didn't require those components to fit our data. But data quality is getting better in the X-rays. One of the things that has been a key area of the modeling recently is that we have to be careful to make sure that we're actually normalizing our models correctly based on the absolute luminosity of the source. There are two there's two key parameters of the models, which is the ionization of the accretion flow, but also the density of the gas. And there should be a one-to-one connection between these, right? The ionization of the layer on top of the disk just depends on the flux that I shine on it and the density of the gas. So there should be some logical connection between these, because we can measure the flux in a sense, right? We can measure the overall luminosity, and then based on some basic physical assumptions about the system and its geometry, we can estimate what the expected ionization and the density should be. And these should be consistent. Again, this is a slightly confusing figure, but what it shows you is that they are consistent because there's quite a lot of uncertainty, mostly in the density of the disk. But it's important to benchmark spin estimates with this kind of thing. Otherwise, we're energetically incorrect. Okay. The next recent development in observations of X-ray observations of black holes broadly, but mostly from a reflection point of view, is that we think when you go to this soft spectral state, okay, so what you're looking at here is an observation of a system that's in its soft spectral state, and it's mostly dominated by the low energy X-rays, by the soft part of the spectrum, the disk, and then some small tail of high energy X-rays coming from this corona, right? And here, what we noticed is that, our traditional idea of this reflection process was that the corona is somewhere near the top of the disk. It's got all the high energy photons, so that's the stuff that gets reflected. But there can be situations where the emission from this accretion disk far outweighs those high energy photons from the power law, and actually we could be seeing photons that are coming from the inner part of the disk and returning to the disk itself. So this is encouraging for us, because this allows you then, if you have a good model for this, which we're still trying to work on, we have a basic model for it, but we need a more complete model for this. You can try to again, it's this consilience thing. You can try and measure spins during the different spectral states if you have a more accurate model. Now, I made this point before that the choice of model and when we apply it can probably will bias spin measurements. And this is an example of what I mean. If I apply this model to this data set versus this one, I'm going to get a different estimate of spin. So we need to be sure that we're accurately representing the underlying continuum. And this is just a diagram to show what I was referring to. That we have photons from the inner regions of the disk that actually get returned to the accretion disk. And by the way, this is a very easily predictable phenomenon in GR. We know this has to be there. We're just not sure that that's what we're seeing in the data. We think that's probably what we're seeing, but the actual emission has to be present. And there's another, I think, really interesting recent development as well that refers to plunging gas. Okay, so gas that's already gone through the ISCO and is now falling into the horizon of the black hole. Does that play a role? Okay, and this matters because, as I mentioned at the very beginning, right, we make these spin estimates by assuming that the disk has reached the innermost stable circular orbit. Now, if it's recessed from that position, if it's truncated, and I measure spin and the spin is say 0.5, then that's a lower limit on spin because the actual ISCO could be closer in. This is the opposite effect, right? If I have material that's falling through the innermost stable circular orbit, and for whatever reason, we had previously thought that this emission wouldn't matter, but what if it does? What if the photons that reflect off that gas actually do appear in the data? They're a prominent enough signal. Then this will cause spins to be biased in the opposite direction. The main point here, right, is just that if we discount this effect, we can be biasing ourselves to higher spins, and that effect matters for lower spins. We're still working on. I won't go into the details of this one, and I'll leave my conclusions here. Thank you.